Doesn't this scene seem dull without the colour? Colour has a profound influence on how we perceive our surroundings. To understand more about colour and how we see it, we're going to identify two stages. How we recognise a particular quality of light reaching our eyes as a particular colour, and secondly, how that quality of light is produced in the first place. How then do we recognise colour? This man, Isaac Newton, made one of the most important discoveries about the nature of colour. Rainbows had fascinated Newton like many others before him, and the observation that rainbow colours could be observed when light shone, for example, on soap bubbles or through cut glass ornaments, were well known before his time. So what was it that Newton achieved that no one else had? In his famous experiment, he put a prism in a beam of light, and so produced a spectrum. Nowadays, we know that it's the shorter wavelengths that are most strongly refracted and the longer wavelengths that are least refracted. And this section of the electromagnetic spectrum, the visible part, extends from about 400 nanometers in the violet end to about 700 nanometers at the red end. And in the green part, it would be around 500 to 550 nanometers, and the yellow would be around 600 nanometers. Now, in Newton's time, the prevailing view was that the prism actually introduced the colours. But Newton was convinced that it was the prism that was sorting out colours that were already there in the white light. If I now bring this small mirror round into this position, I can pick up the spectrum reflected in the small mirror, carry it over to this large spherical mirror, and that concentrates the light into that white spot. We can show the effect rather more effectively by putting on this glass globe, which mixes the colours together, and you can see that the result is white light. Well, the next important discovery was about 150 years later by Thomas Young. And this is what he did. I have here 3 slide projectors that can produce different colours: a blue, and a green, and a red. Now, watch what happens if I overlap these colours. Red and blue give this reddish blue colour that we call magenta. Blue and green give this blue-green colour that we call cyan. Now, what about green and red? Well, surprisingly, they give yellow. And if we now add the blue so that all 3 colours overlap at the centre, there we get white. And furthermore, if I vary the proportions of the 3 colours at the centre there, we can produce almost any colour we like. Now, this principle that we can produce any colour by mixtures of 3 colours we call trichromacy. And the 3 basic colours, red, blue and green, we call the additive primaries. Your colour TV set works on this principle. The front of the screen is covered with triads of tiny red, blue and green dots or lines. And the actual colour you see depends on the relative intensities of these 3. Now, why should trichromacy work? Young decided that the answer must lie in the eye itself. But if each identifiable colour had a special receptor adapted to it, there would have to be hundreds of different kinds of receptor. And the sensitivity to any one particular colour is almost the same as that to white light. This led Young to believe that the eye uses trichromacy. In other words, that the eye has just 3 kinds of colour receptor, and the colour we see depends on the relative extent to which these 3 receptors are stimulated. Well, as you saw in block 1 of the course, we have in the retina 2 different kinds of cell. These are called rod cells and cone cells. The rod cells are sensitive to very low levels of light, but not to colour. It's the cones that are sensitive to colour. In effect, Young was suggesting that we must have 3 types of cone cell. But it's not until very recently that scientists have been able to look directly at their colour sensitivity. One person who has done this is Dr. Jim Bowmaker of Queen Mary College.
When you look at a piece of retina through a microscope, you can very easily distinguish the cones from the rods. But in a piece of human retina, all the cones look the same. And if we want to look at differences between the cones, we need a more sophisticated method. We use a system where we pass a small beam of light through the cone outer segment and measure the amount of light that the cone absorbs at each wavelength. And the apparatus here is designed for that purpose. At the back, we have a light source which passes light into a monochromator. This is a device for splitting light into its individual wavelengths. And we can control which part of the spectrum we're looking at with a wavelength drive here. We also have attached a motor so that we can scan from one end of the spectrum, the red, through to the other end of the spectrum in the blue. In front of the light beam, as it comes out of the monochromator, we place 2 slits to produce 2 small beams of light about 1 millimetre in size. These, of course, are still far too big to pass through an individual cone. But just as you can make an object larger by viewing it through a microscope, if you pass the light in the opposite direction through a microscope, you can reduce the size of an object. The beam of light from here passes through a plane mirror and up through what is in effect an inverted microscope. So that on the microscope stage, we produce 2 tiny beams of light, some 500 times smaller than the beams we produced here. On the microscope stage, we mount a specimen of retina squashed between 2 glass slides and align it so that one of our tiny beams of light passes through the cone. The amount of light that the cone transmits is then collected and measured by a detector attached to the microscope. Of course, to do the measurements, we have to work in darkroom conditions because the photosensitive chemicals within the cones will be damaged by the light that's illuminating the room. The 2 bright spots that you can see are the 2 beams that are some 500 times smaller than the millimetre beam we started with. The bottom beam, which I can block with my finger, like that, is going to be the sample beam which we will put into the cone. The top beam, that one, is the reference beam. The cone we're going to look at is just below the 2 beams, and I will line up the photosensitive part of the cell with the sample beam like that. And we're now ready to record the absorption spectrum, and I'll switch on the drive. The plotter is now drawing a graph of the absorbance of the cone against wavelength. We've gone from the red into the blue part of the spectrum, and it will now reverse and come back from the blue to the red. In the normal room lights, we can now see the curve that we've plotted. In the longer wavelengths, the cone is absorbing very little light, but in the middle wavelengths in the spectrum, it's absorbing considerably larger amounts of light. But at short wavelengths again, it's absorbing very little. We've recorded then a cone that is most sensitive to the middle wavelengths of the spectrum, a cone that's commonly called a green cone. This, of course, is only one cone, and I've already surveyed a number of cones and recorded 2 other types that are on tape, and I can play them back to you and show what these curves look like. The plotter is now drawing A second cone type. This is a cone that's sensitive to the red part of the spectrum and again is commonly called a red cone. We're now drawing the third cone type, and you can see that it absorbs light in the short wavelength parts of the spectrum but absorbs very little light at longer wavelengths.
Three types of cone, sensitive to red, green and blue. What could be simpler? Light with wavelengths above 620 nanometers stimulates mainly the red cones. Light of wavelength 500 nanometers stimulates mainly the green cones. But when both are stimulated to similar extents, the brain interprets the effect as yellow. But we don't need a mixture of lights to make yellow. These sodium lamps appear orange-yellow, but here the light is monochromatic with a precise wavelength of 589 nanometers. But because the cone response ranges overlap, this wavelength stimulates both red and green cones simultaneously, and again the brain interprets the result as yellow. Trichromacy is a simple and elegant theory, but it doesn't explain everything that we see, or should I say perceive. Just try this experiment. Focus on the center of this object and keep staring at the screen. Now what do you see? I saw an equally improbable pink elephant. The white screen should have caused all three cone types to respond equally, but the green cones were fatigued, and so the main response came from the red and the blue. Now, is it possible, in fact, to match all colors by mixtures of the three primaries? Is there, for example, such a thing as brown light? Here's an experiment to demonstrate that. There's a yellow patch on the screen, and I can control the level of illumination of the patch and of its surroundings separately. And if I find a level so that the patch itself is less brightly illuminated than the surroundings, you can see that the patch looks distinctly brown. And there's another patch adjacent to it which is in fact brown. And you can see that very clearly if we put the studio lights on. So the answer is that brown is merely dark yellow, and it's all a question of the relative levels of illumination, and trichromacy certainly doesn't predict that. Now here's another experiment that illustrates the power of the brain in interpreting the colors of a scene. We've taken three black and white pictures of a still life scene. This one was taken through a red filter, and so the white parts just show the red content. This one was taken through a green filter, and so the white parts show the green content, and this one was taken through a blue filter to show the blue components. Now I'm going to put on color filters on the appropriate projectors. This is a red filter, this is a green filter, and this a blue filter. And now if we add the three projections, trichromacy should predict that we would get the original colors of the scene. And you can see that we do get a reasonably good approximation. But now watch this. If I remove the blue component and then take the red filter away, all we have now is a green projector and a white projector. And trichromacy would suggest that we should only see shades of green. But in fact, I can see quite clearly, especially on the pepper, a distinctly pink color, and the bananas look quite yellow. That is an effect known as the land effect. So the colors we see depend partly on their relationships to each other within the same scene, and even to some extent on the colors that we expect to see. Modern theories cope with these effects in terms of physiology and psychology, That is how the signals from the cones actually reach the brain and are processed there. Nevertheless, trichromacy explains the beginning, how we begin to recognize a particular set of wavelengths as yellow, red, green, or whatever. But how are these wavelengths produced in the first place? So far, we've been mixing colored lights. But what about objects? How, for example, does a red dahlia produce red light? Well, of course, it doesn't actually emit red light. It's illuminated by a white emission source, which in the normal way would be daylight. So how do objects appear colored? Let's see what would happen if we remove some of the colors of the spectrum from our synthesized white light. There's the spectrum again, and what I'm going to do is to eliminate just the red part, round about 600 to 700 nanometers, and you can see that we have a blue-green color. If we eliminate the yellow and green part from the spectrum, round about the 500 to 600 nanometers, we get a magenta color, and that's of course formed by the blue and the red parts of the spectrum. And then if we eliminate the blue round about the 400 nanometer region, then we have yellow light. Well, let's just go through that sequence again. Eliminating the red part of the spectrum gives us a blue-green. Eliminating the green part of the spectrum gives us a magenta, and eliminating the blue part of the spectrum gives us a yellow. So now, what can we say about this dye solution? Why does it appear blue? Well, you can see the answer if I put it in the spectrum. You can see, I think, that it absorbs most strongly in the red region of the spectrum. And the remaining colors, the greens and blues, pass on, and so the bowl corresponds exactly with the color of the dye. We can get more precise information about absorption using a spectrophotometer. This high peak means that the dye absorbs red light. And as we get to the green at about 550 nanometers, the absorption has dropped off. And there's almost no absorption at all in the blue. Here's the trace redrawn for clarity. For comparison, here's the intensity distribution of the wavelengths, which is the inverse of the absorption curve. That is the transmission spectrum. And the most intense transmittance is in the blue region. Well, that's fine for clear solutions, but most objects don't transmit any light at all. This piece of cloth was colored with the blue dye, and it still absorbs light. It absorbs in the red and orange region, but it doesn't transmit at all. And so to see the color, we have to come round to the front and look at the reflected light. The spectrophotometer we saw earlier can be adapted so that it will measure the absorption of surfaces. Light is sent down flexible fiber optic guides to a device called an integrating sphere. In this way, we can record an absorption spectrum of our blue cloth. As we'd expect, it absorbs most strongly in the red region. The absorption falls off rapidly below about 600 nanometers, and it subsequently absorbs virtually no light at shorter wavelengths. This, then, is the absorption spectrum of the blue cloth. Light which isn't absorbed is reflected, and so the reflected wavelengths show an inverse relationship to the absorption curve. And this is known as the reflection spectrum. As you'd expect, a red tomato absorbs very little at the red wavelengths, but does absorb green and blue light. So here's the reflection spectrum of a red tomato. But is this the distribution of reflected wavelengths which reach our eyes when we see a red tomato? Well, not quite. We've forgotten something, and that is the spectral distribution of the incident light. A theoretical white light source would have a spectral distribution like this. Practical white light sources have equally broad spectra, but the intensity distribution is by no means even. Here's the distribution for a tungsten lamp, and here it is for daylight. So the quality of light reflected from a tomato will depend on whether it's illuminated by tungsten light or by daylight. But we tend to experience the same sensation of colour regardless of the illumination, and this indeed is one of the drawbacks of trichromacy. The lighting on either side of this screen is different. On this side, where it's yellow, we can still see most of the colours. But if I move over to the other side of the screen, where the illumination is sodium street lighting, which you remember is almost monochromatic, the distribution, the spectral distribution, is so narrow that we're only seeing shades of lighter and darker yellow. So colour sensation is really the eye and brain's response to a particular combination of wavelengths. And that combination is usually produced by selective absorption from the incident light. Let's now summarize the whole process with a familiar object. The main pigment in carrots is a substance called beta-carotene, whose absorption spectrum shows a maximum in the blue region at around 450 nanometers. So the carotene transmission spectrum, which is the inverse of that, shows a maximum at red wavelengths. The reflection spectrum of the carrot, due mainly to the beta-carotene, is therefore rather similar. It peaks in the red region, although it reflects wavelengths in the green region to a lesser extent than carotene. Here, redrawn, is the reflection spectrum of the carrot, but this was measured in light from the integrating sphere. What reaches our eyes is slightly different, because daylight does not have equal energy at all wavelengths. It's slightly blue. This spectral distribution stimulates the red-sensitive cones most, then green cones, and then blue cones. Signals from these and from cones stimulated by the background are integrated by nerve cells on the way to the brain. There, processes that are beyond the scope of this program will establish in the consciousness that the carrot is orange. The absorption of light energy by the carrot, and by most coloured matter around us, doesn't lead to any changes in that matter. There are exceptions, and one is much more important than any of the others, and there'll be more about that later in the course.
On Sunday the 29th of April at the same time.